Hey everybody, in this video and in this chapter we're going to be talking about inference on categorical data. Specifically, we're going to be talking about goodness of fit testing. So let's talk about our chi-square distribution. We learned about this in the past, but remember that it's not symmetric. Its shape depends on the degrees of freedom, just like when we were learning about t-distribution. And as the number of degrees of freedom increases, it becomes more symmetric. So based on this image, we've seen this in the past as well, but if you notice down here, the degrees of freedom is 30, and then you can see this bell-shaped or symmetric type curve that we get. And then the value of chi-square are always non-negative, so it can always be 0 or more. And so what we're going to be talking about here is our goodness of fit test, and what this is it's basically a procedure used to determine whether a frequency distribution follows a specific distribution. So we're using this test to figure out if the distribution we're looking at follows a specific distribution. All right, so now let's talk about what's called an expected count. And we need this because it goes into our formula that we're going to use for our goodness of fit test. So suppose that there are n independent trials of an experiment where there's 3 or more mutually exclusive outcomes. Then P sub 1 is our probability of observing the first outcome. E sub 1 is the expected count of that first outcome. Outcome 2, we use a subscript 2, and outcome 3, subscript 3, and so on. So then our expected counts, which is what we're denoting E sub something, is going to be just n times our p-value. So for the first outcome, it would just be n times p1. And we can denote that as mu as well, mu sub 1, and then that's our expected count, E sub 1. So let's find our expected counts using this example. One growing concern regarding U.S. economy is the inequality distribution of income. The data in this table represent the distribution of household income for various levels in the year 2000. An economist wants to know if the distribution of the income is changing. So she randomly selects 1,500 households and obtains their income. Find the expected number of households at each income level, assuming the distribution of the income has not changed since 2000. So just looking at our table real quick, we have income all the way from under 15,000 to 200,000 or more, and then the percent of the population that makes that amount of money. So then our first step is that the probabilities are going to be our relative frequencies. And so remember how that works. It's just going to be our percents, but in decimal form from our table. Then the expected counts for each income are as followed using what we just learned about. The formula for our expected count is just n times p. So we do this for all of our outcomes. And so for the first one, it was our sample size 1,500 times our probability for under $15,000 of income, which is 0.099, and we get 148.5. So that's our expected count value. And then we just do this for each of the outcomes. So for the next one, 1,500 times the probability that the income is between 15,000 and 24,999. We get 147 as the expected count. So we can keep doing this for each of our outcomes. Okay, and so we'll just multiply our sample size times our probability, and then we can note that of the 1,500 households surveyed, the economist expects to have 148.5 households that earned under 15,000, 147 that earned between 15,000 and 24,999, and so on, assuming the distribution of the income has not changed since 2000. So our numbers that we got was our expected counts, and then so that's what we could say that economist expects as far as household numbers earning that income level. So now here is our formula for our test statistic for our goodness of fit test. So that's why we were learning about this expected count E, because it's going to go right here in our formula. So our test statistic here is going to be chi squared, and in the formula, remember capital sigma is summation, we're adding, and so what we want is O sub I minus E sub I. This is just our observed counts in each category minus our expected counts. We take that number and square it, and then we divide by the expected count. And then we do this for each of our outcomes or categories, and we add those all up. And that's how we compute our test statistic. And then this approximately follows the chi-square distribution, where we have k minus 1 degrees of freedom. But this is only true if the following are satisfied. Number 1, all expected frequencies are greater than or equal to 1. So that means our E sub I values are 1 or more. And number 2, no more than 20% of the expected frequencies are less than 5. Okay, and so just note, our formula for our expected count is n times p. Alright, so a goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population. So that's what we're going to be doing in the rest of this video. Now, if you want to compare 2 or more populations, you have to use another test. It's testing for homogeneity, which we don't actually cover in this section. So our goodness of fit test, here's the test. And so step 1, determine the null and alternative hypotheses. Remember, H sub 0 or H naught is your null hypothesis. And in this case, it's going to be that the random variable follows a certain distribution. And then our alternative hypothesis, H sub 1, is that the random variable does not follow that distribution mentioned in the null hypothesis. Step number 2 is going to be to determine your level of significance, alpha. Step 3 is to calculate your expected counts, E sub I, which we did in our last example. And then part B of this would be to verify that the requirements, 1 and 2 that we just looked at, for our goodness of fit test are satisfied. And so it's just that all expected counts are greater than or equal to 1, and that no more than 20% of the expected counts are less than 5. And so if, just a caution here, step 3b is not satisfied, one option that you can actually do is to combine 2 or more of the low frequency categories and put them into a single category to go ahead and satisfy that 3b criteria. And then continuing, part C, compute your test statistic. So our test statistic is going to be denoted chi sub 0 squared or chi naught squared. And it's just our formula that we looked at already. Once we have this test statistic, the next thing we want to do is look at our critical value from our chi-square distribution table. So you're going to use a chi-square distribution table. Based on alpha, you're going to get your critical value, chi sub alpha squared. And you get that from the table also looking at your degrees of freedom, which is k minus 1. So we'll go through all this. And then you compare, once you have your test statistic and your critical value, you compare them to each other. If your test statistic is greater than your critical value, you reject the null hypothesis. And then last, you state your conclusion. So this was the steps if you do the classical approach. We're going to go ahead and start over at step 3 and talk about the p-value approach. So starting over at step 3c, you still compute your test statistic, chi naught squared. And then when you go to your chi distribution table, this time you're looking for the p-value, which is actually your area under your curve. So it's the probability or the area under the curve. And that's also going to be based on your k minus 1 degrees of freedom. You can also use technology instead of the distribution table to get your p-value. And then step 4, this time you're comparing your p-value to alpha. And if your p-value is less than alpha, that's when you reject the null hypothesis. And then we state our conclusion. So let's try this out with this example. So similar to our last example, in terms of income distribution, the economist still wants to know if the distribution of income is changing. So she still selected their 1,500 households and obtains the household income shown in our next table. And then it contains the expected counts under the assumption the distribution has not changed since 2000. That's what we computed in our first example. And so the question is, does the evidence suggest that the distribution of income has changed since 2000 at the 0.05 level of significance? And so note, the data in this table is based on the 2017 current population survey, but it's been adjusted for inflation. So here is our table. So we have our income levels and our observed counts, and then our expected counts that we computed earlier. So step 1, our null hypothesis is always no difference or no change. For us, for this example, it means no difference in the distribution of income between the year 2000 and today. So we're looking for the sample evidence to show that the distribution is different today. So our null hypothesis is distribution of household income is same today as it was in 2000, and alternative hypothesis is that it's different today. So then our level of significance was given, 0.05, and we move on to step 3. We already computed our expected counts previously, and we have them in our table. And then step 3b is satisfied because remember, all the expected counts had to be greater than or equal to 1, but they're all at least 5. And then also, no more than 20% could be less than 5. So because they're all greater than 5, it satisfies both 1 and 2 from step 3b. Now we move on. We're doing the classical approach first to compute our test statistic, chi-naught squared. So we're going to plug into our formula. So this is by hand. A lot of times you can use technology so you don't have to do this by hand. But notice what we have. Each of our observed counts minus our expected counts. We square that value and we divide by the expected count. So because we had 9 income categories in our table, or you can think of it like 9 trials, we had to do this 9 times. And we add all that up and we get 20.693. Okay, and then step 4, there's 9 categories. So our critical value is going to be based on 9 minus 1 degrees of freedom, or 8 degrees of freedom. And so we have chi sub alpha squared. Remember, alpha was given as 0.05. So we can go to our distribution table for chi squared to get 15.507. So let me take you over to that table real quick and show you how to get this number. Alright, so here is our chi-square distribution table, and we have 8 degrees of freedom, so we're going to go down to row 8, and then our level of significance was 0.05, so we'll go to that column and then line those two up, and then that's how we get our 15.507. Okay, so what we want to do is compare our test statistic of 20.693 to our critical value that we just found from our table, 15.507, and notice that our test statistic is in the critical region, or it's greater than the critical value. And so because of this, we reject the null hypothesis. And so then we can say, in conclusion, the sample evidence suggests that there is sufficient evidence at the 0.05 level of significance to conclude the distribution of income in the United States is different today than it was in the year 2000. Okay, so let's do this again, but using the p-value approach. So starting over at step 3, we compute our test statistic, chi-naught squared. We're still going to get the same number, 20.693. Now we're going to go to our distribution table, and we're going to work with our chi-naught squared value of 20.693. And so then what we'll find, I'll take you back over to that table in just a minute, is that our value, 20.693, it's closest to 20.090 and 21.955. So it's between these two numbers. And then the areas corresponding to those numbers are 0.01 and 0.005. And so we can conclude that our p-value is between 0.005 and 0.01. So let's go over to that table real quick. Okay, so we have 8 degrees of freedom, so we're going to be in this row, and we're looking for the number closest to 20.693. And so if you go across that row, what you'll see is it's going to be over here in the between the last two. I can't really highlight it, but it's in between these last two values right here. And so if you go up from there, the corresponding areas or probabilities is 0.01 and 0.005. Now, because we have a p-value between two values, to get a more accurate estimate of what the p-value would be, or calculation, what we want to do, or can do here, is actually use technology. So we'll go over to StatCrunch next, and we'll get that our p-value is actually 0.008. So let's do that real quick. Okay, so what you want to do is enter your observed counts and expected counts into two separate columns. And then once you've done that, we're going to go to Stat and down to Goodness of Fit. And we're going to do chi-square test. Okay, so then we have to select our observed column, which I labeled observed, and our expected column, which I labeled expected. If you don't relabel them, it'll just say like var1 and var2. And then we just go to compute. And then there we have it. And so notice what we have. Our degrees of freedom was 8, and our p-value is 0.008. Okay, and so a p-value of 0.008 means if the null hypothesis is true, we would expect about 8 samples in 1,000 to yield the results at least as extreme as those we obtained. And so, based on our results here, the observed results are unusual under the assumption the null hypothesis is true, and that's because the p-value is less than our level of significance. 0.008 was less than 0.05, so we reject the null hypothesis. And then we have the same conclusion that we got from our classical approach. All right, let's try one more. So an obstetrician wants to know whether the proportion of children born on each day of the week is the same. She randomly selects 500 birth records and obtains the data shown in this table. So we have our days of our week and then the frequency of births based on those days. Is there a reason to believe that the day on which a child is born does not occur with equal frequency at the 0.01 level of significance? So step 1, our null hypothesis is our statement of no difference, which in this case would be that we assume the day on which a child is born occurs with equal frequency. And so H0 is that the probability of being born on a Sunday is the same as the probability of being born on a Monday, and so on, which is all 1 out of 7. And then our alternative hypothesis would be that this is different, so at least one of these proportions is different from the others. Our level of significance was 0.01. And then step 3, our expected counts for each category, which is our days of the week, assuming the null hypothesis is true, is n of 500 times p, which is 1/7 for each of them, which is 71.4. And then checking our criteria, we have that all expected counts are greater than or equal to 5, and so our requirements are satisfied, so we can use our goodness of fit test. So then we move on and calculate our chi-naught squared, our test statistic, for each of our categories. And so we just take our observed count minus our expected count, square that, divide by our expected count. We do that for each of our categories, and we get 19.568. We have 7 categories, so our degrees of freedom is 6, and so our corresponding critical value for chi sub 0.1 squared from our chi-squared distribution table, we would get 16.812. And so notice that our test statistic at 19.568 is in our critical region, or it's greater than our critical value, so we reject the null hypothesis. And we can conclude there's sufficient evidence at the 0.01 level of significance to reject the belief that the day of the week on which a child is born occurs with equal frequency. Now, doing the same thing with our p-value approach, we have 7 categories, degrees of freedom is 6, and our p-value you can get from your distribution table or from technology. You're going to compare that with your 19.568 test statistic. Our p-value is going to be less than 0.005, and if you use technology, you're going to get that it equals 0.0033. And so because the p-value is less than the level of significance, we reject the null hypothesis, and then we get the same conclusion we had before. Okay, so that's it for this one, talking about the goodness of fit test. Thanks for watching.